Hey everybody, welcome back. In this video we need to talk about Coulomb's Law. If you remember, a Coulomb was a fundamental unit of charge, and it's one of the electrical force is one of the fundamental forces that we need to understand, and Coulomb's Law will help explain that to us. So the interaction between charged objects is a non-contact force, and it acts over some distance of separation. So the electric force, like all forces, is typically expressed using the unit of newtons. And being a force, the strength of the electrical interaction is a vector quantity that has both magnitude and direction. The direction of the electrical force is dependent upon whether the charged objects are charged with like charge or opposite charge, and also upon how far apart they are, or their spatial separation. So determining the direction of the electrical force vector, it's actually pretty simple. If both of your objects have the same charge, you're going to have a repulsive force, and if they have opposite charges, you're going to have an attractive force. There's three factors that affect the force of the interaction between the charged objects. You have to have two objects at least, so the charge of the first object makes a difference, as well as the charge of the second object, and then the square of the distance that's between them. This is an inverse square relationship, and that's signified by this 1 over r squared symbol. So getting down to it, Coulomb's law states that the electrical force between two charged objects is directly proportional to the product of the quantity of charge on the objects, which is what the Q stands for here. So the electrical force is directly proportional to the charge on the objects, and it's inversely proportional to the square of the separation of the distance between them. And so R here just signifies the difference. Now you notice there's a constant K here, and the symbol K is a proportionality constant that's known as Coulomb's law constant, and we're not really going to discuss that too much in this course. It will just give you a value for that proportionality constant. So this symbol K, as we said, is a proportionality constant, and it's known as Coulomb's law constant. And this value depends upon the medium that the charged objects are in, or that they're immersed in. Well, we're only going to be dealing with air. So in the case of air, the value is about 9 times 10 to the 9th newtons meters squared divided by Coulomb square. All right, and so the symbols here, the symbols Q1 and Q2 in Coulomb's law equation represent the quantities of charge on the two interacting objects. R represents the distance, and K is Coulomb's constant. And if you're wondering what the E is, this is the electrical force. So this subscript of E just tells you that this is an electric force. All right, and you guys may not want to write all this in your notes, but you need to pay attention to what I'm saying here. You know, I'm always make a big deal to you guys about using the proper signs and using the units, and the units are important, but listen to what this says about the sign that we use. When we use positive and negative signs in the calculation of force, the result is always going to be negative, because a positive times a negative is a negative. And so that a negative sign is always an attractive force, and a positive value is going to be a repulsive force, because whether you're multiplying two positives, you get a positive, or if you multiply two negatives, you get a positive. And so mathematically, the force value will be found to be positive when they're of like charge, and the force will be negative when they're of opposite charges. So this is consistent with the concept of opposites attracting and like charges repelling. Just keep that in mind, because when we're doing the math, you may want to leave the positive and negative out of the equation until the end. That'll save you sometimes. Another thing to keep in mind here, 1 Coulomb is that's an enormous amount of charge. You have no idea. So it's more likely that Q values that you're going to realistically find are 10 to the negative 9th or 10 to the negative 6th coulombs. That's a lot more reasonable. So for this reason, we use Greek prefixes for these. So charge is expressed in units of micro coulombs, and so there's your little symbol for micro. and nanocoulombs. So if a problem states the charges in these units, it's just a good idea to convert to coulombs prior to putting it into the equation. And so here's all it is. A microcoulomb is 10 to the 6th, and 10 to the 9th nanocoulombs is, there's your symbol for that. All right, so let's do an example. Then you can get down to this. So we've got two balloons that are charged with an identical quantity and type of charge, and it says it's negative 6.25 nanocoulombs, and they're held apart at a separation distance of 61.7 centimeters. So determine the magnitude of the electrical force of repulsion between the two. Why don't we start by writing down what we're given here. So the givens that we have here, we know that Q1 is going to equal, it says, negative 6.25 nanocoulombs. All right, and Q2 is the same, negative 6.25 nanocoulombs. And we know we've got a separation distance of 61.7 centimeters. And let's remind ourselves what K is. If you remember writing this down, K is 9 times 10 to the 9th Newton meters squared Coulomb squared. And we're trying to find the electrical force. But if we take the advice, let's convert these nanocoulombs. So it's pretty simple. This is going to be negative 6.25 times what? Times 10 to the 9th coulombs. Negative 9, excuse me. And so charge 2 will be negative 6.25 times 10 to the negative 9 coulombs. Now you got to pay attention to the distance here too, because this is in centimeters and we need to be in meters. So 61.7 centimeters, divide that by 100, we get 0.617 meters of separation. And so now we've got all the units that we'd need to be able to solve the problem. And let's go to the next page and do that. All right, so if we start with our equation, like I always advise, the electrical force is expressed by this equation. And all we have to do is fill in the blanks. So the electrical force is going to be 9 times 10 to the 9th Newton meters squared Coulomb squared times, and remember we're going to drop the sign while we're working the problem here. So we're just going to put in 6.25 times 10 to the negative 9th coulombs times the same charge, 6.25 times 10 to the negative 9 coulombs. We have to divide this by our distance, which was 0.617 meters, and remember we have to square this, so you guys keep that in mind. Now just to make sure our units are working, we've got the coulombs cancel, and we've got meters squared and meters squared, so the unit that we have left is newtons, which should be right. If we put all this in the calculator and crunch the number, we should get a number of 9.23 times 10 to the negative 7 newtons. And we need to remember that this is a repulsive force. All right, so that would make it a positive number. All right, that wasn't too ugly. Let's work another example. Let's do the same thing. Let's start with what we're given. All right, we're told here the charges are a little different. So Q1 in this example is 3.37 micro. Oop, didn't do a very good job on that symbol. 3.37 microcoulombs. Charge 2 is negative 8.21 microcoulombs. So let's see. We got those two charges, and we've got an attractive force. So the electrical force on these two is 0.0626 newtons. And remember again, K was 9 times 10 to the 9th Newton meter squared Coulomb squared. All right, now let's take care of these units again up here. So if we convert microcoulombs to coulombs, let's see what we get. This is going to simply be 3.37 times 10 to the negative 6 coulombs. And so this would be negative 8.21 times 10 to the negative 6 coulombs. All right, and I forgot to put in here in our problem. This says this was these are opposites, so we have an attractive force, and so that makes these newtons, makes these negative. All right, let's go to the next page, see what we can do here. If we start with our original formula, the electrical force represented by this equation, but we're trying to find the separation distance, so we're going to have to rearrange our equation. So let's see how we might do that. Let's get rid of this r squared over here. So the electrical force times radius squared would be equal to this expression. And we want to get r by itself. So let's go from there. Let's divide by the electrical force. So that'll give us r squared equals this expression. And we just want r, so we're going to have to take the square root. Yeah, so the algebra on that's pretty simple. All right, so now all we have to do is stick in some numbers and see what happens. Let me get this little smaller so we can see what we're doing. Okay, let's put these numbers in here and see what we can get. So r is going to equal the square root of some big stuff here. K is 9 times 10 to the 9th Newton meter squared Coulomb squared times, and what was our first charge? 3.37 times 10 to the negative 6 coulombs, and we got to multiply that times 8.21 times 10 to the negative 6. Running out of space here, and dividing all of this by the electrical force, which is 0.0626 newtons. All right, so let's see what we do here with our units. Newtons here look like they're gonna cancel. Coulombs look like they're gonna cancel if I put it in over here. And we're going to be left with meter squared, but we're taking the square root. So from this then, if we take a look at what happens, we're going to have the separation distance between these should end up being a positive 1.94 meters. Because when we take the square root of meter squared, we get meters. So there you go. The math really is not all that ugly. I hope you followed through with any of this. If you have any questions, ask me in class. And we'll see you later.